Hello, health science students. This is Professor Van Dyke with your Week 9 video. We're going to cover radiation and its prevention, so make sure you read the PowerPoint on that. It will be on the exam. There will be materials from this PowerPoint that will be on your exam on Thursday, so make sure you're ready for that. I've already posted the study guide, so make sure and read the study guide. A couple of important dates that are coming up. So obviously midterm 2 is this Thursday, October 22nd. And then week 10 and 11, your paper and presentation are due as well. And at the end of this video, I'm going to give an announcement. So make sure and watch the whole thing. That can benefit you in regard to your paper and your presentation. Okay, so with your paper is due week 10, actually your presentation is due week 10 as well. But again, at the end of this presentation, I will give you a short announcement in regard to rewarding you for watching these videos. So we are talking about radiation, but do keep in mind Thursday you do have your exam. There is a study guide for that, so make sure and read it over. So radiation, its control, slide 1, we're going to talk about the introduction, the importance, radiation types, ionizing versus non-ionizing, very huge difference, radiation sources that are natural and human-made. We're also going to talk about microwave and UV radiation as well. On to slide 2. So radiation refers to an emission or propagation of particles of waves as energy. So it's going to be releasing this energy propagation through particles that are being released. The process involves an emission of radiation, and this is what's known as radioactivity. So what's essentially happening is nuclides, so atoms, they're undergoing spontaneous disintegration. So they're breaking down and releasing this emission source of radiation. And they're essentially what's happening is they're disintegrating into simpler forms so that they can maintain stability, and this is the process that's occurring. So that's why you see things like uranium, plutonium. They're unstable, and they're releasing spontaneous disintegrative elements so that they can become more stable. So a health impact for humans certainly is that exposure can result in mutations, birth defects, cancer, death, lots of different things that can happen when you're exposed to radiation. So you're probably familiar with Chernobyl. The first responders in Chernobyl, almost all of them are dead because they were involved in one of the largest releases of radioactive material and radiation in any given time in history, that they were actually exposed to that. But certainly a lot of problems that came from that. We'll talk about that later in the lecture. On to slide 3. So when we're dealing with radiation types, we have non-ionizing and ionizing radiation. Ionizing radiation is really the bad one. Of course, non-ionizing radiation in the appropriate dose can be very dangerous as well. And certainly when we think about ionizing radiation, and when we talk about toxic substances, again, like with Agricola, what he said was the difference between medicine and a poison is essentially the dosage. So obviously we use ionizing radiation still today to treat cancer, but at the same time, too much ionizing radiation can be very dangerous for an individual. So with ionizing radiation, we're talking about alpha, beta, X-ray, gamma. So these are going to be the ionizing radiation, which are going to have much more of a strong effect on the human form. And then you have non-ionizing radiation, which can be dangerous, especially in very high doses. So UV light, obviously visible light, infrared waves, and microwaves as well do produce non-ionizing radiation. Same as your cell phone. So the area around the antenna pickup on your cell phone is going to produce a very small amount of non-ionizing radiation. So again, not something you want to ideally be exposed to quite a bit, but something that you want to try and minimize as best as possible to protect yourself. On to slide 4. So lots of sources, certainly natural, cosmic, and earth materials that are going to produce ionizing radiation. So with naturally occurring sources, this can be found in the background, really. If you walk around with a Geiger counter, you might be surprised in some areas that you would pick up ionizing radiation sources that can come from the air, water, the soil, and even food at times. So definitely a lot of natural sources. But we also have cosmic radiation as well. So these are high energy electrons and protons that are coming from outer space and also from the sun as well, this cosmic radiation. At low sea level, it's much less, but as you increase in elevation, it can continue to jump. So certainly it doubles with each 2,000 meter increase in altitude. So as you get into higher elevations, you really want to protect yourself from that cosmic radiation source, especially if you're like a mountain climber, things like that. And it can be responsible for about 25% of all spontaneous mutations. So cosmic radiation can definitely do some damage, especially in higher elevations as you continue to increase elevation up to 10,000, 12,000, 14,000 feet. And then we also have earth minerals as well. So these are naturally occurring. Certainly uranium, thorium, and radium, and potassium that's found in the soil, rocks and coal, brick houses that give more radiation. So definitely a lot of earth materials that we can stumble across. Uranium isn't something that we make in a lab. Uranium is something that we dig out from the ground and then we utilize it in things like nuclear energy, most certainly with nuclear proliferative bomb materials, things like that. It can be very dangerous, dirty bombs and things like that. On to slide 5. Continuation of radiation sources, ionizing radiation sources. So we have radionuclides in the body, substances that we can pick up through water, food, and through the air. And water and air get these particles from rocks, and food is going to tend to get it from the soil. So if you have soil that has radioactive sources that are producing ionizing radiation, it can absorb into the food. And then we have enhanced natural sources as well on slide 5. These are natural sources that have been affected by human activities like uranium milling. In the past, we were much more careless in regard to how we were milling things like uranium, phosphate mining, and certainly jet air travel. But radon gases in houses and mines as well. So if you have a house, most specifically in the Midwest, and you have a basement, and that basement has cracks in the surface, it has cracks that run through it, it can actually leach radon gas into the house, and this can come through pipes and things like that as well. On to slide 6. How does radon enter the house? So if you do have a house in places like the Midwest, you'll notice that it's going to be coming up through the bedrock. As we've mentioned before, that this is a naturally occurring source. It comes through the bedrock and through the soil, and then it gets into the well water, through the fittings, through your sump pump in the basement, through cracks in the foundation. It can come up through your shower, things like that. So that's why in the Midwest you find a lot of houses will have radon detectors actually in the homes. On to slide 7. More sources for ionizing radiation. So we have a lot of human-generated sources like medical applications. So certainly with X-rays, and as we'd mentioned, radiopharmaceuticals in regard to treating cancer. But we also have nuclear weapons fallout, like nuclear testing is going to release things like cesium-137 and strontium-90. And certainly, just so you know, I mean, we do still test nuclear weapons, not so much here in the United States, but, maybe 5 years ago, India and Pakistan were getting ready to tee off on each other, and they certainly were testing nuclear materials, and there were some fairly large signatures in regard to nuclear testing in those countries. But we also have nuclear power plant emissions as well. So certainly we have nuclear power plants that are all across the country. They're very easy to find. We certainly still have San Onofre here. We used to have Diablo Canyon, which is now shuttered because it couldn't pass its NRC, as you remember, the Nuclear Regulatory Commission's inspections, so they just went ahead and closed it down. But we do still have a lot of nuclear power plants as well, and the emissions from these locations can produce ionizing radiation. And then we also have consumer products like radium and diols. Unfortunately, these are older consumer products that you tend not to see, but we do still find Americanum in smoke detectors, and then X-rays at airport screenings. You can still find some older systems at some of the older airports that will produce ionizing radiation. And then thorium and gas lantern mantles and things like that, which can still be fairly dangerous. So slide 8. Just to give you a little bit of general information, when we talk about dosage for radiation, we're dealing with radiation absorption doses, the RADs we call them, and this is a unit mass that is going to be identified when we look at how much material someone has actually absorbed. And then the international unit is going to be gray, which is essentially 100 rads. Radiation in humans is expressed in seviers, which is an absorbed dose. So again, radiation absorption dose, the rads, are going to be expressed in seviers or millisieverts generally. And that's going to give us an idea of essentially how much of the radioactive material has been absorbed by an individual. And we talk a little bit about this. This isn't something that I generally tend to make too many test questions on because it gets a little bit complicated, and you've all had physics already, so I assume that you know roughly what we're talking about here. The average whole body radiation exposure from all sources in the U.S. is 0.01 millisievert. Sometimes that ends up being a test question. There's very little evidence that this is going to have any general health effects on people, so it's not something that we're too concerned about. So 0.01 millisievert per day is essentially your radiation dose that the average individual is being exposed to. But when we talk about RADs, radiation absorption dose, you'll see that here very shortly when we talk about some modeling that came from the Fukushima Daiichi power plant disaster that occurred in Japan. So on to slide 9. Radiation-induced effects. So higher doses are extremely dangerous. They can cause damage to biological function and features, including mutation to genetic material, birth defects. So remember teratogens. So certainly radiation can have a teratogenic effect. Infections, hemorrhages, cataracts in the eyes, certainly leukemia, cancer, hemorrhages, all kinds of really bad stuff with regard to radiation when you have an exposure that is substantially higher than the 0.01 millisievert, which we average out for most humans on a given day. Larger doses will directly kill cells, so that's why we use radiation to kill cancer cells, where small doses damage the genetic material, resulting in mutations in cancer. So, obviously both of these are very bad, right? So high-level radiation to a whole body dose of greater than 1 sievert over a short time results in symptoms that can range from nausea all the way up to death, depending on the dose. So radiation can be very, very damaging for an individual. And as I mentioned before, we do still use this for radiological medicine. And obviously, it's a very important thing. And if you have cancer, you know how important radiation is for that process that will eventually heal you. So again, very important to remember that the dose is going to differentiate medication from a poison. On to slide 10. More health effects continued. Mutation. So there is no threshold below which mutation will not occur. If you're exposed to radiation, you're going to have mutations. And birth defects, you will definitely have birth defects when exposed to radiation in much higher doses, specifically in areas of reproductive material. It's one of the reasons why when you go to the dentist, they'll put that heavy lead vest over you that will generally cover that area as well. And then with cancer, there's a direct linear relationship between leukemia and X-ray exposed dosages. So again, that's one of the reasons that we do these very sparingly. X-rays are done, from your dentist. You're only going to get them once a year, and generally you can go your whole life if you do it right and not have any X-rays for broken bones and things like that. So the federal standard for exposure is 1.7 millisievert per year. And as you remember, for us, we're at 0.01 millisievert per day. So 1.7 millisievert, which is going to exclude things like medical exposure, maximum permissible radiation dose for the general public. So occupational exposure is going to be higher at about 50 millisievert if you work in places like the nuclear power plant and places like that. So you really have to be careful in selecting your job. This is one of the reasons why we've built the environment very differently for X-ray technicians. Now they're in a completely different room because we try to minimize their exposure to radiation, to ionizing radiation. And this is very important. When I was a kid, the dentist used to stand right next to me when they were giving X-rays, and he would do that for 30, 40 patients a day, and certainly they don't do that anymore. They remove those individuals from the facility, from that room, and they go to a room that is going to protect them from the ionizing radiation. So on to slide 11. This is something that becomes interesting in slide 12. So again, radiation is not radiation. Radiation is all the same. Absolutely not. It's not the case. And you can see that here with beta radiation, which is an ionizing form of radiation, and alpha radiation, which is also ionizing, are very different. So 3,000 rads, radiation absorption doses from the beta radiation, is going to equal 30,000 millisevere. But if you look at the alpha radiation, 3,000 rads of alpha radiation is going to yield 600,000 millisieverts. Very, very different. 30,000 to 600,000 is a substantial difference. So this becomes important on the next slide, which I'll show you here shortly. So again, just some general information. The federal standard is 1.7 millisieverts per year. Occupational exposure at 50 millisieverts, and the average whole body radiation exposure from all sources in the US, 0.01 millisievert. So you compare that to a dose from alpha radiation, a substantial dose at 3,000 rads equaling 600,000 millisieverts. It's fairly extraordinary. So why do I bring this up? We move on to slide 12, and this is going to give you a really good idea. Now, this was a model based on the release from the Daiichi nuclear power plant in Fukushima, Japan. So when they had the tsunami, it destroyed the power plant, and this was the subsequent release from Fukushima in regard to beta and gamma radiation releases. Now, fortunately for us, this was not alpha radiation, because if you look, in day 3, it was already hitting the Bering Sea and at 3,000 rads. So as you remember, 3,000 rads of beta radiation equals about 30,000 millisieverts, which is way beyond the 1.7 millisieverts which we're used to being exposed to. So what a huge dose of radiation given modeling. Now again, modeling isn't perfect, but after 3 days, you can bet that it was fairly close to this. And then if you look at 6 days, it was still at 1,500 rads of beta radiation, which was going to be an exposure of, right around 15,000 millisieverts. 15,000 millisieverts that was about to hit the coast of the United States 6 days after Daiichi blew. Now, that's fairly interesting. I mean, when you think about what we talk about on the news in regard to science and things like that, did anybody hear anything about this at all? And I'm going to venture a guess and say no. But the fallout still remains, right? There are fish that are still being very heavily dosed, certainly bluefin tuna and things like that swam this route consistently. They're still finding high doses of radiation in fish and things like that. But certainly for us, here on California on the West Coast, I mean, after 6 days, we were about to get hit by somewhere in the area of 1,500 rads of beta radiation that was coming from Daiichi. On to slide 13. So everybody's heard of Chernobyl in the Soviet Union, and this was a really a massive. This is one of the worst environmental disasters in human history. They had a meltdown that was triggered by a test that they were running that got out of hand. And before they knew it, they had a massive meltdown and an explosion in one of the cooling towers, and that reduced, it released iodine-131 and cesium-137. Cesium-137 was definitely the worst because it's, I mean, Chernobyl, all this time later, is still an absolute ghost town. You can't go into these areas without having a full suit on. There's a wonderful documentary, I think it's on Netflix, about how the original casing that they wrapped around it to try to control its release of radioactive material had begun to decay, and they built a huge, massive structure over the top of it. So basically a crypt for the Chernobyl disaster, but horrible, horrible stuff. The people that lived in these areas suffered extraordinary health effects. And as I mentioned before, the workers that went into these areas to try to eliminate these sources of radiation releases and try to control it. Most of them died very quickly. So slide 14, this is some of the health effects that we've seen. Some of the environmental health effects, catastrophe, obviously, the whole area had to be completely removed of life. And unfortunately, you can't tell wild animals not to go into these places. So a lot of things still happening in those areas. But 300,000 people were forced to move. And obviously they wanted to move because they were within 30 kilometers of the plant itself. That's a huge dosing for a large population. How did it affect these people? And generally what you see was an increase in thyroid cancer, was very common in Belarus and the Ukraine and Soviet Union as well. So in the photo on slide 14, this is a grandfather and his grandchild. Both of them are suffering from thyroid cancer. You can see by the gauze around their neck there. So some believe the stress of the accident was actually almost harder on people than the radiation, because, I mean, it's terrifying. When you have a release like this, it's going to have a lot of effect on the individual psyche of the people that live in those areas, and certainly the fear of wondering if you were going to die from cancer and things like that was very stressful for these individuals. On to slide 15. So what do you do with radiation? How do you prevent and control it? So a couple of key pieces here. Exposure time, the shorter the better, right? You do not want to be exposed to this stuff. And with the first responders in Chernobyl, I mean, they just kept working and they died because of it. So you want to be there as short a period as possible. That's why we get so few dental x-rays, right? Short time, quick burst, we're done, we're gone. And then distancing yourself. So the farther from the radiation source, the better. Like with Chernobyl, we just moved everybody out, and that was the strategy for Chernobyl, the distance, get them further away. And then the quantity. The lesser the amount of radiation you're exposed to, the better. Quantity. That's why we don't have x-rays on our teeth twice a year. We want less exposure to these radiation sources. And then certainly shielding. We want to have outer clothing that protects us from the particulates, and the high density shielding material should be made of things like lead. That's going to protect from the waves that are being produced by these ionizing and non-ionizing radiation sources. So we want to shield ourselves from these sources. On to slide 16. So you all remember that nuclear waste is handled by the NRC, the Nuclear Regulatory Commission. So high-level waste is going to come from spent fuel from reactors. It's extremely dangerous. It will penetrate and create heat, and it's not to be handled directly by the human hand or come anywhere close to you. I mean, high-level nuclear waste is extraordinarily dangerous, and it's still very reactive. So definitely something that we don't move far. So with radioactive sites, places like the power plants, like San Onofre, they're not going to drive high-level waste down the road because it's extremely dangerous. So they're going to store that on site at the nuclear facilities. But we also have low-level waste as well, which is something that you can come in contact with at your hospitals. So it's going to be contaminated clothing, cleaning solutions, wiping rags, industrial materials, even bedding and clothing of patients that are getting radioactive medicine. And they can be environmentally hazardous, and they could take 100 to 200 years to decay to where they are actually harmless. So low-level waste is handled in very specific fashions. Some of it goes to secure landfills, some of it's incinerated, but we deal with them on a case-by-case basis. And if you work in a hospital, make sure you are well familiar with the process of dealing with low-level waste. Otherwise, you'll end up running into massive fines from the EPA and the NRC. So slide 17, we're going to quickly discuss non-ionizing microwave radiation. So this is a shortwave. It's used in radars, and obviously for us, lots of different things, TV transmitters, satellites, telephones, walkie-talkies, garage door openers definitely, but certainly in our microwaves in the house as well. So they're going to excite the particles, and that will generate heat. And that is a non-ionizing form of radiation. So obviously nowhere near as dangerous as ionizing radiation. So when I was a kid, they used to tell us, don't stand by the microwave. Still to this day, I do not stand by the microwave because there is this non-ionizing radiation source. On to slide 18, continuation of microwaves. So they absorb the microwave radiation, and that causes vibrations in the molecules. So the molecules begin to move, and as they're moving, they're gonna generate heat, and that's how your microwave essentially works. They're absorbing microwave radiation, they're exciting the molecules are moving, and that's producing heat. So it's a low frequency energy, and it can pass through the body without being absorbed. And then with regard to intermediate frequency energy, which also can be produced from microwaves, this is going to be absorbed by the deeper tissue without noticeable heating of the skin. And this can actually cause bodily harm. So something you want to try to avoid. And then the maximum permissible level of microwave radiation is 10 milliwatts per square centimeter of body area. So certainly this is something they keep in mind when they build things like microwaves. So some of the health effects for microwave, most susceptible to microwave injury is going to be the eyes, most certainly gastrointestinal tract, testes, urinary bladder, gallbladder, and these can develop things like cancer and cataracts, chromosomal aberrations and birth defects, even heart attacks as well. So something that you really want to try to avoid as much as possible. So you remember, how do we avoid this? You stay away from it, you limit your usage, you stay as far away as possible, you shield yourself from it, and these are things that you can do to help yourself. Slide 20 is UV, ultraviolet light, which can be very helpful. So obviously we use UV light now to kill viruses and bacteria in hospitals. I've seen some fascinating stuff with robots that can do these things, but we certainly want to limit our exposure to UV light. And UV light can definitely be the source of non-ionizing radiation. The key takeaway here is that it can target, the target of ultraviolet light damage is going to be your DNA. So you definitely want to limit your exposure to UV light as much as possible. On to slide 21. So ultraviolet light can obviously produce skin cancer. So basal cell carcinoma and squamous cell carcinoma account for about 1/3 of all cancers, mostly found in exposed parts of the body like the face and the neck. But they're treatable, and if they're diagnosed early, they're very treatable with a high success ratio. And these are going to be from exposure where you're constantly being exposed to the sun, the sources. So this is one of the reasons that you want to wear sunscreen as much as possible. Now, number 2 on slide 21 is malignant melanoma, which is much less common. And this is going to come from when you get like a really severe burn. Some of us only go to the beach like once a year, and we get that just really bad sunburn one time a year, like on our back. And this is the thing that's going to develop into malignant melanoma if you do it frequently. So you want to definitely avoid that as much as possible. And then on to number 3, so ultraviolet light causes drying and mottling, premature wrinkling of the skin. If you know a truck driver, ask them if they can, essentially put their arms together so you can see the difference between the side that is exposed through the window and the side that is not, and you'll notice that UV light does have an effect on those individuals. On to slide 22, a little fun fact. So cell phones do emit radio frequency energy, which is called a radio wave, which is a form of non-ionizing radiation from their antenna. The tissues nearest to the antenna can absorb this energy. So if you put your cell phone in the same exact place every time, don't do that. And this is just my advice to you. You can find peer-reviewed journal articles that say, yes, cell phones can be dangerous, and you also find the same the exact opposite where they say no, cell phones are not dangerous. So keep that in mind. We're kind of being test subjects, and if you put your phone, like I know people that exercise at the gym, they always tuck it into their bra. Don't do that. Just don't take the chance. That's my advice. So that is the slide material for radiation and its control. Definitely be ready for your exam, which is this Thursday. I will definitely release the exam early, same as I did with exam 1. There won't be any surprises. It's going to be the exact same kind of test. You'll have the exact same amount of time to do it, so make sure you have it done before midnight on Thursday. Now, here's the deal, okay? You have week 10 and week 11 to do your paper and your presentation, right? It's due week 10. It's due at the start of week 10. But because you watched this presentation, I will give you through week 11 to finish your paper and your presentation. So that gives you an extra week. If you watch this video, you get an extra week to do that, okay? Now again, if you have it done, turn it in to me and say, hey, I watched the video, but I just want to, get your feedback on this. Is this good enough? I will grade it and read it over and give you advice if it's not good. But chances are you guys are going to do great on your papers and your presentations. I'm not worried about it. And what I'm going to do is, so that you can view some of these through week 10 and week 11, so you can see how other people did theirs, I will post them. If you don't want yours posted in Blackboard, just let me know and I won't post it, okay? So again, hopefully you watched this video for week 9. This is radiation and its prevention. Your midterm is going to be this Thursday, October 22nd. And then your papers and your presentations are due week 10 and week 11. Okay, so make sure and get those to me. With that, have a wonderful week. Send your questions to william.vandyke@csusb.edu. And I look forward to your papers and your presentations.